this is, let's see, 12.7, number 7, right, to where we're given this equation, rho equals sine of theta times sine of phi. All right, and what we want to do is try to figure out what this shape would be, right? And for me, if I can turn them back into x, y's, and z's, that makes it a little bit easier. I mean, we have some shapes that I asked you guys to know off the top of your head. Like if I said to you, if I said to you rho equals some type of a constant, right? Remember that's a sphere. Right? If I said to you that theta equals some constant, that was a half plane. If I had phi equals some constant, then that was a half cone, either above the z-axis or below the z-axis if it were above or below pi, or pi over 2, excuse me. So this one doesn't quite fall into those categories, so let's see if we can somehow get an idea of what they're going to look like. Okay. All right, so what I'm going to do is to try to turn these things into x's, y's, and z's. First thing I'll do is I'm going to multiply by rho. Right? And the reason I'm going to do that is because on the left-hand side, I now get a rho squared, and on the right-hand side, I'll get a rho times sine theta sine phi. Right? And what's handy about having a rho squared over here now? How can I substitute that out? Anybody remember what was our sub for rho squared? You bet. And then if you notice this right-hand side right here, that's one of our direct substitutions as well. What could I substitute that out with? Yep. So if I pull everything over to one side here, I've got x squared plus y squared minus y plus z squared equals 0. Right? So when you see this, what shape should you be thinking about right here? And the hint is we've got 3 squared terms there. They all have the exact same coefficient in front of them. All 3 of them have a 1 in front of them. Right? So what shape is that going to be? You bet. Okay. Now, if I want to get a little more information, what I could do is I could try to complete the square on these y's to get the center and radius and all this other stuff. So remember, if you complete the square, what you do is you look at this number that's in front of the y, which in this case is a -1. You take half of that number, square it, and add it in to complete the square. So on the left-hand side, I've added in, I guess, a fourth. So I'll add a 1/4 over here to the right-hand side. And then what I'm left with is an x squared. And then this is just y minus 1/2 squared plus z squared equals 1/4. Okay. So now when we look at this, it's a sphere. The center is at 0, 1/2, 0. And the radius, well, if that's r squared, then the radius is 1/2. Okay. So this equation that we've got right here, that's the same thing as that sphere. All right. Does that make sense, Jack? All right. Anybody else have a question about number 7? All right. Well, let's look at number 8. I'll just get it set up because it's kind of the same thing. All right. So for number 8, we're given rho equals 2 cosine phi. What I'll do here again is to multiply both sides by rho to give me a rho squared equals 2 rho cosine phi. And then this rho squared is this substitution again. And what's 2 rho cosine phi? Anybody remember that one? Oh, I'm sorry, not 2. Just let me do this. What is rho times cosine of phi? It's just z. Right? So then I could pull everything over to one side again. And again, what shape is this going to be? 1x squared, 1y squared, 1z squared. So that's a sphere again. And if we complete the square on the z's, let's see, that's z squared minus 2z. If I take half of that number, which is -1, and square it and add it to both sides, I'm really adding a 1 to both sides. So then I've got this on the left-hand side equals 1. So the center here is at 0, 0, 1, and the radius is just 1. All right. So you all good with 7 and 8? All right. Anything else from the first part of 12.7 then? Let's see. For 14, we're given these two equations. Rho is less than or equal to 2, and rho is less than or equal to cosecant of phi. Okay. All right. Now this first one, that's one of those where I kind of asked you all to be able to look at that and see what's going on. Like if I said to you rho equals 2, what shape is that supposed to represent? You guys remember? Yeah. So that's a sphere with radius 2, right, centered at the origin. Right? So if I could, and again, forgive me, I'm going to try to draw this thing. Right. All right, so that's what that one looks like. Now, what about this one? Might have to manipulate this just a little bit. Right. So let me remind you of a couple of things. Remember how we could substitute x out with rho sine phi cosine theta, and y could be subbed out with rho times sine phi sine theta? So x squared is rho squared sine squared phi cosine squared theta. Y squared is rho squared sine squared phi sine squared theta. Right. So if we add those two together, x squared plus y squared, right, I would get this thing. Right? And if you factor out what they have in common, they both have a rho squared, they both have a sine squared phi, and that leaves me with cosine squared theta plus sine squared theta, and of course that's just 1. So x squared plus y squared is just rho squared times sine squared phi. Okay. All right, so why is that important? Well, what does rho equal to cosecant phi look like? Well, cosecant is the same thing as the reciprocal of sine. And then if you multiply both sides by sine phi, I get rho times sine of phi equals 1. Right? So now go back to this equation. I have x squared plus y squared equals this. So if I take the square root of both sides, I get rho and sine of phi here. So I could substitute that out with the square root of x squared plus y squared equals 1. Okay. All right, and in 3 dimensions, then if you recall, this equation, x squared plus y squared equals 1, that's actually just a cylinder that goes up the z-axis that has a radius of 1. Right? So this had a sphere of radius 2, so if I had something of radius 1 inside here and did a cylinder that went straight up and straight down, like this. Right? Of course, this thing just represents, this is the whole cylinder, so this represents the upper half of that cylinder, it looks like. Okay? So if I had to draw this thing, it says to, let's see, let me get back to the right page. It said to sketch the solid. So it would just kind of be this part, that part of the cylinder that's used inside that sphere. So I've got the base of this cylinder, goes like this, and then it's got this hump part from the sphere that looks like that thing. So it looks like it is this silo looking thing, if I sketch it out properly. Right. So that's kind of what it looks like for 14. All right, Jack, was that yours too? Yeah. So if I had to scan again, my drawing's terrible, but if I had to sketch it out, that's kind of what it looks like. It's this cylinder that's on the inside of that sphere that kind of goes up that z-axis, and then it intersects. It's probably not as pronounced as this thing, but it intersects that cylinder right there. All right. So any questions about 14? All right. Any of those others from the first part of 12.7? Let's look at number 22, right, in our book. Right. So this one says we want to evaluate this triple integral over some region, and the triple integral, or at least a formula we're going to use, is 9 minus x squared minus y squared, and we will integrate over the volume of that region. Okay. And in this case, the region we're looking at is the hemisphere. Right, so it's half of a sphere, even though I really can't spell it. Hemisphere, I think is what I spelled, of x squared plus y squared plus z squared is less than or equal to 9, and z greater than or equal to 0. Right. So we know x squared plus y squared plus z squared equals 9 is that sphere at the origin with radius equals 3. What does the less than or equal to part bring to the table here? So again, we know the equality part gives me this sphere of radius 3. That's the equality part. So what does the less than or equal to part give me? Any guesses, any thoughts? Well, it's all a part inside the sphere, right? So it's the solid ball. So it's not just the outer edge of the sphere, it's the whole thing, right? And then for z greater than or equal to 0, that's just the upper half of this sphere, right? So there is no bottom half for this sphere. Okay, so let's see if I can find the right thing. So this part's not going to be on there. So it basically looks something, if we were on the xy plane, it's this hemisphere type of thing. Okay. All right. So what we want to do is to rewrite this triple integral using the spherical coordinates. So if you remember, what we do is we take our function and we'll substitute it out using rhos, thetas, and phis. Right? And then the extra stuff we have over here was a rho squared times sine phi, and then d rho, d theta, d phi. Okay. So how could I rewrite this part? Let me do a little scratch work down here. Let's see. X is the same thing as rho times sine phi times cosine theta. Right? So there's x squared. Y is rho times sine phi times sine of theta squared. Right? And if I factor out this minus sign, we've got this rho squared sine squared phi cosine theta plus rho squared sine squared phi sine squared theta. And if you remember, we already saw this once today, right? We saw that when we were, where were we? Oh, right here, right, for this part, right? So this simplified into just this when we factored it, okay? So this part I could just write as rho squared sine squared phi. Okay? So for the triple integral, this part I can rewrite as 9 minus rho squared sine squared phi. Okay? And then I have all this additional stuff from our substitution method, which gave me a rho squared sine phi d rho d theta d phi. Okay? So now we need to just figure out the bounds for each of those integrands. Okay? So let me clean off some of this. All right, first of all, for rho, that's just the little links here. If I start here at the origin, the smallest value for rho that I'm going to have is 0. And in any direction, no matter how far out I go, I'm going to go a distance of 3 if I go all the way to the edge. So that's going to go from 0 to 3. Okay. Now let's think about, how about phi for a second? All right, so this integral right here. If I start here on the z-axis, right, at that very top point, I don't have to rotate off of it at all, right? So I don't have to rotate any degrees. So the lower bound for phi is going to be 0. And then if I rotate all the way down to that, let's see, xy plane, I'm going down an angle of 90 degrees, which is pi over 2. Right? And then for theta, if you look at theta, we've got a big old circle in my xy plane here that I'm going to rotate all the way around that circle. Right? So the value for theta goes from 0 to 2 pi. Okay? So it looks like that is a way that we could set up this particular integral. Right? And then we can simplify it just a little bit. Right? So I could rewrite the inside part as 9 rho squared, whoops, because remember, it should be like this. I kind of wrote it wrong. Right? Times, or minus, I'm sorry, rho to the 4th sine cubed phi d rho d theta d phi. Okay. All right, so this is how we could rewrite that integral using that spherical coordinate model. Okay. All right, so 2 questions I need to ask you all, and again, I can't see you, so give me a voice answer. Don't just shake your head. But do you see how we went, first of all, from the rectangular coordinates into the spherical? And then the second question would be, do you see how we got the bounds for each of those? Right. So any questions on either of those 2 parts? Or are you all okay with it? Yeah. Yeah, that one actually, that's a good question because that's actually the toughest one to find, at least in my mind. It is, just because we haven't used it very often, so we're just not quite used to it. Right? So if you remember, the idea for phi is that if I've got some point over here in the xyz plane, right, to where maybe I came over x, down y, and then up z to get to there. Right? If I start here on the z-axis, how much anglage did we have to rotate over, right, to get to that point, right? So that's what phi is. Okay? So for this particular picture, remember we've got our hemisphere here. Right? So again, apologies for my artwork, but if I've got this hemisphere, right, then if you think about all the points that we have to cover in this hemisphere, this point is right on the z-axis, right? And if you're right on the z-axis, you don't have to rotate it at all. Okay, so that's where the 0 part is coming into play. Right? Now, what about a point that's down here, maybe on the y-axis or on the x-axis, or somewhere down in here? If I start here on the z-axis and I rotate all the way down to there, how much have I rotated? Right? Well, that would be 90 degrees. Right? But in terms of radians, how much is, let's see. Yeah, how much is 90 degrees in terms of radians? Pi over 2. Okay, so that's how you can get those bounds. And that's why, I mean, a picture can be pretty handy if you can draw one, at least a good picture. Of course, if you draw one like me, it might mess you up a little bit. But yeah, pictures can help you out in determining those values. But do you see how I got the lower bound and the upper bound for phi, Ethan? All right. Anything else from 22 on the conversion to spherical or finding those bounds? Um, let's see. If you look to your, well, actually, look behind you real quick. Um, and I'm sorry, what was your question again? Oh, okay. Just checking because I couldn't quite make it out. I wasn't sure what you were saying. All right. Anything else from 22? Nice catch, by the way. By the way, if we had to integrate this thing, sometimes it's separable to where we could factor the phis and thetas and everything away from each other and just do one part at a time. In this case, we really can't. And just as a reminder, how would you all handle sine cubed? Right, because you'll see some of these things in your homework, right? How would you start to integrate sine cubed right there? Do you remember our technique for that? To where I would write it out as maybe sine squared phi times sine of phi. And then the sine squared, I could substitute that out with 1 minus cosine squared phi times sine of phi. And then this becomes a u sub, because I could say let u be cosine of phi, and then du is minus sine of phi. So this becomes 1 minus u squared, and then this becomes a negative du. Right. So you may need to go back and remind yourself how to do some of these different integral techniques. All right, so last call for 22. Anything from there we can straighten out before we look at another one?
There is no active call.
All right, excellent. I think Alexa heard me again. Let's do one more of these things. Let's look at 28. All right. So 28 says to find the volume of the solid that lies within the sphere. Let's see. X squared plus y squared plus z squared equals 4. Let's see. Above the xy plane and below the cone z equals the square root of x squared plus y squared. Okay. All right, so again, in terms of my picture, this is a sphere of radius 2, centered at the origin. What's it mean if it's above the xy plane? What shape are we going to have? Well, if it's above the xy plane, that's all the values where z is bigger than 0. So this actually is another one of those hemispheres that we had right there. And then this cone, goes out like this thing, right? Because it's the upper half of that cone. If it were a negative square root of x squared plus y squared, it would open down. Okay? But it's not, so it's the one that opens up. Okay? So what I want to find here is the volume of the solid that lies within the sphere and below the cone. Okay? So if it's in the sphere and below the cone, it looks like it's this part in here. Okay? All right, so let's see if we can set this up. All right, so if you remember, the way we can find a volume using a triple integral is by using the number 1 right there. Right? Because if you recall, if I integrate a function, right, if I integrate a line, that gets me an area. If I integrate an area, that gets me a volume. Of course, in area, we could use the original function, right? So a double integral can also give me a volume. Or we turn that into a triple integral by taking this function and kind of rewriting it on the integral somehow, and then just using the number 1. Right? So if we're going to use a triple integral to get a volume, we want to set it up like this. Okay? So let's see, clean this up. All right, and again, since we're going to try to do this using the spherical coordinates, don't forget about these extra multipliers we need out here, this rho squared sine phi, and then let's integrate with respect to rho, theta, and phi. All right, so let's think about these different bounds. Okay, think about rho right off the bat here. What's the smallest and biggest values that we're going to get for rho? Right? Like if I start right there at the origin, what's my value for rho? How far have I traveled from the origin? Well, I've traveled 0 if I'm still there. But then if I go all the way out to the edge of that hemisphere, that's when the value for rho will get as big as 2. Okay. All right, let's see. Now, what about theta? If you notice, again, if you think about theta for a second, how many of these angles are we rotating around? All of them. Right? So I'm going from 0 to 2 pi. And then what about phi? Right? What does phi run to and from? Okay. Let's see. Yeah. So if I can maybe draw this picture from the XY plane's point of view, it kind of looks like this thing, right? This would be the hemisphere, right? And here was the cone, right? And we wanted the area underneath it, right? So in other words, this part is gone, and I've got all of this stuff we've got here. Okay? So now what happens if I maybe try to throw that z-axis in here? If I start here on the z-axis, how far do I rotate to get to that line right there? Because remember, this is just that right circular cone. So what angle do we hit at right there? 45 degrees, you bet, right? And if I go from here all the way down to there, what's my angle for phi? That's 90 degrees, right? So 45 degrees gives me pi over 4 in terms of radians, and then 90 degrees gives me pi over 2 in terms of radians. Okay? So this is how we could set up this particular volume if we needed to find it. Okay? And if you notice, this is one we actually could factor apart. So let me just show that to you real quick. Well, actually, before I do that, any questions on how we found those bounds for 28? Because in this case, we're just asked to find a volume, right? And the way you find a volume with triple integrals, that was the little argument I was trying to go through before, where if we integrate a line, right, that gives me an area. If I integrate an area, that gives me a volume. Of course, this area, I could substitute it out with that integral of the line. And if I took the line and put it on a third integral, I could just use the number 1 there to find my volume. Right? Sure, we could find a volume using a double integral like this thing, right, using f of x type of a thing. Or we could set it up like this and use a triple integral. In this section, since we're working with triple integrals, that's the route that we're going to try to use. Okay. All right. So, any other questions on how we came up with those bounds? You guys see how we got rho, theta, and phi? In this particular case, yes. If we tried to do it like in the x, y, and z plane, we could have set up maybe a double integral. And maybe, I guess the top function would have been the cone minus the bottom function. And then we could try to set this up using, what, disc and washer or shells or cylinders to find those things. And again, trying to integrate something like this, well, this part wouldn't be too bad, but trying to integrate this thing, yeah, that's just not going to work out well. So being able to rewrite it like this actually made it pretty handy. Okay. Let's see. All right, but again, any questions on how we got those bounds? All right, so just to show you, this thing actually is separable. I could rewrite this integral, since they're all have really nothing to do with each other. I could make this the integral from 0 to 2 of rho squared d rho, and then the integral from pi over 4 to pi over 2 of sine of phi d phi, and then the integral from 0 to 2 pi of, well, there's nothing there, just a d theta. Right? And then I could find this answer, find that answer, find that answer, multiply them all together, and that would give me my total. Right? Or you could just go one integral at a time and get your answer that way too. Okay? But the previous one that we had here, there was no way to separate the rows from the phi's, so we couldn't do it for this one. But for this one, we could actually separate them and write it like that. Okay. All right, so any questions on those two examples? Either 22 or 28, right? So this was number 28 in the book.